some Poisson distribution examples. Engineers are creating an expensive system that relies on a component with a failure probability of 0.32, and 6 of them are installed in parallel. Okay, if any one of the components works, the system works. So we have these systems, these 1, 2, 3, 4, 5, 6. 6 of them are installed in parallel, or actually not in series, in parallel. So this will not be that. They are installed in parallel. 1, 2, 3, 4, 5, 6. And if any of these component works, the system works. What is the probability exactly? Now the question is, what is the probability that exactly one of these components works? So let's try to solve this. Let X be the number of components that work. Probability X is equal to 1. But what is the distribution of X? So fixed number of independent trials, there are 6 trials, each with the same, so they are fixed number of independent trials, and each with same probability of success. And we are counting number of successes. So that sounds like a binomial problem. So the random variable X will have a binomial distribution with a n of 6 and a probability of 0.68 of success, because failure is 0.32. Now we can use the probability formula of probability of X is equal to X is equal to n choose X, P of X 1 minus P n minus X. So in this case it's going to be 6 choose 1. Probability is 0.68 times X, which is 1, and 0.32 times 5, which comes out to be 0.137. So it is 1.3% that one of this system will work. So the system works if at least one of the 6 components work. So what is the probability of X is more than 3? Because this is the probability that the system, so this is the probability that one of the system works and 5 doesn't work. But what is the probability that it is X is more than 1? Because that is the probability that the system works. It has to be 1 or more, but that is just 1. So now for probability of X more than equal to 1, you have to calculate the probability of X is equal to 1 plus probability of X is equal to 2 plus probability of X is equal to 3 plus probability of X is equal to 4 plus probability of X is equal to 5 plus probability of X is equal to 6. We can calculate all of them and add using the binomial formula. But there is an easier way of doing this, because the possible values of X zero, 1, 2, 3, 4, 5, 6, and so we can calculate the possibility of 0 and then you can subtract that, and that will be the probability of this, because it's either works or doesn't work. So then you can just do 6, choose 0, 0.680, 1.0.686, and 6 choose 0 is 1, and 0.68 raised to the power 0 is also 1. Any value raised to the power of 0 is 1. So it will come out to be 0.99893. Next question is, a union chapter has 32 male and 26 female members. An important committee of 7 people needs to be made. The president says that he will randomly select 7 members. What is the probability that there are exactly 6 women? Now here is the question is, what is the distribution of X? There is 26 successes, which is the females, and 32 failures. But sampling is without replacement, and we are counting the number of successes, right? So sampling is without replacement, and we are counting number of successes. So this becomes a hypergeometric distribution. And in hypergeometric distribution, it is easier to just use the intuition of doing it. So we choose 26, choose 6, and 32, choose 1, divided by 58, choose 7. We can put it in the formula also, but it's just easier to do it in the intuition than trying to put it in the formula. But now if the question is changed to, what is the probability that committee contains at least at least 6 women. Now this would be just probability of 6 or less will be 1 minus probability of 7. When you calculate the probability of 7, if it's not 7, then it's going to be 6 or less. Another question is, a beverage manufacturer puts tiny gold flakes into a beverage container at an average rate of 800 flakes per liter. 1 liter container is randomly selected, shaken, and a 10 ml sample is drawn. Probability that it contains exactly 2 flakes of gold. Here we are counting number of something. We are counting number of something in a volume. Thus it is a Poisson distribution, and lambda is the mean number of flakes in the given volume. mean number of flakes in a given volume, which is 800 flakes in a liter, and so how much is that in 10 mLs? It's going to be 8, right? So 8 flakes is in the mean number. So now probability of x is equal to I is lambda x e to the power minus lambda divided by x factorial, which is going to be 8 2 because we want to have exactly 2 flakes, and then e to the power minus 8 divided by 2 factorial, which is going to be 0.0107. There is about 1% chance that we get 2 flakes in the sample. Next question is a European roulette wheel has 18 red slots, 18 black slots, and 1 green slot. Ball is equally likely to land in any of the, so there are total 37 slots. Ball is equally likely to land in any of the 37 slots. What is the probability that the first time ball lands in the red slot occurs in 5th spin? So again, let x represent the number of spins needed to get the first red. Here we are interested in the first success. We are interested in the first success. So thus it will have a geometric distribution. Number of trials needed to get the first success is the geometric distribution. Number of successes in trials, in n trials, is the binomial distribution. So this is the number of trials needed to get the first success. So this is the geometric distribution. So now we first need the probability of failures, which will be 1 minus p raised to the power of probability of failure, which will be 1 minus p raised to the power of times the failure occurs. So probability of x is equal to little x is going to be 1 minus p x minus 1 times p, because this is the formula for the geometric distribution probability. So what is the probability of success happening is, because we have 18 red slots out of 37, so this will be 1 minus 18 times divided by 37, and x minus 1. So x is 5th spin, we want to know, so that will be 4 times probability of success, that is 18 over 37, so that is 0.0338. This thing here is the formula for the geometric distribution. Now we can also ask the question, what is the probability that the first time ball lands in a red spot occur at some point after the 6th spin? The question is probability that the first time ball lands in red spot occurs at some point after the sixth spin. Now in this case we have the probability is x is more than 6, so that is going to be probability of 1 minus x is less than 6. This can also be intuitively calculated as what is the probability of one failure. The probability of one failure is going to be, what is the probability of success? The probability of success is 18 over 37. So probability of one failure is going to be 1 minus 18 over 87. The probability of the second one is also a failure is 18 over 37. So, or you can say it is 1 minus 18 over 37 to the power of 6 is going to be your probability of 6 failures. So probability of x is more than 6 is going to be 6 failures, and that would be your, that it is going to land after the 6th spin, because first 6 are going to fail. The other question is Tom is part of a production process that makes an expensive of instrument. Probability of mistake by Tom is 0.001. But when Tom makes an error, he gets rattled and likely to make more errors. What is the probability that Tom destroys exactly that Tom destroys exactly 3 of the next 20 items he works on? Here we have fixed number of trials, right? 20. So the trials is fixed at 20, and we are counting number of successes, which we can say that Tom destroying a piece is equal to 3, and we have the probability of destroying individual piece. But it seems binomial, but the problem is that these are not independent. Thus probability of mistake we know, but he does more mistakes once he make one mistake. So this question cannot be answered and needs more information. And one of the practical reality is that not every random variable has a simple nice distribution. More often our probability model is an approximation of more complicated underlying reality.